hold on. Come on, computer. You can do this. There we go. So if you've not, oh, this is not right. That is not the right outs. It is not the exit slide. It is these. Those were the ones from before. What was this? Yes, this is fission versus fusion. I put the wrong thing on here. Let me fix it. Let me fix it. All right. We already did the exit ticket. We did it together. All right. So, right in, y'all. Hush. Right. So, this really should not take long. I am hoping that, because there's only 8 of these. I mean, it looks a little complicated, but basically you're adding or you're subtracting. Like, it's not anything chaotic at all. For this opener, let me turn the light off. What is the charge of it? Well, first of all, what is an alpha particle? No, what's an alpha? No, pay attention. What is an alpha particle? What is it? What? No. In radiation, what is an alpha particle? In radiation, we've got alpha, beta, and gamma. Stop throwing things. I didn't say you were. Jimmy did. I saw it out of the corner of my eye. No, I have a 9-year-old child.
She was looking down at the.
So I mean, yeah, we've got 3 things. We got alpha, beta, and gamma. Okay, what is an alpha? What is it composed of? What is it? Which element is it first? No.
It's, yeah.
You just did this. What is this? What is it made up of? It's an element on the periodic table. Helium. Okay. I didn't hear helium. So what are the numbers?
2, 4.
Which one goes where?
2, 4.
No. 4 on the top. Okay, so this means it has a mass of 4 and it has 2 protons. So what is its charge? No. Positive 2. Okay, a beta. What is the letter for a beta? No, an E. And what are the numbers for it? 0 and -1. So what is its charge? -1. Okay, and what is a gamma?
Y.
It's Y. It's really supposed to be this weird symbol, but it's easier on Google Slides to use a Y. And what are the numbers?
0.
So what is its charge?
0.
0. Okay, so that's the answer. But we won't be able to write on this yesterday in the 8th period. I had to restart my computer because my little smart tab vanished, but I can write on it right now. So alphas are positive, specifically positive 2. It's 2 protons and 2 neutrons, which are neutral, no electrons. A beta is essentially an electron. Okay, both of these actually change the number of protons from a parent or a daughter, depending on which way we're going. A gamma doesn't change any of the numbers because a gamma is nothing but pure energy. It has no mass. It is pure energy. That is what is emitted from our sun. What we're protected by our magnetosphere. Without it, we would have an atmosphere and we would die.
She's lying to you. We do not need an atmosphere.
We do too. But we do like Mars.
Never even seen the atmosphere before. I can breathe just fine.
I've seen it. I've seen it skydiving. I've seen it. You can see it if you go up high enough. It is. All right, so we are doing fission and fusion. Y'all, shh, hush. Literally have one more subject for the entire year. Y'all, hush. Stop. Stop it. So fission, this is what we do in nuclear reactors on Earth. Okay, now there is an exception to that. Okay, when you think of a nuclear reactor, you think of if you've ever seen The Simpsons, you got these like cooling towers. Like that. They got these little buildings over on the side, and there's a river that feeds it. It's got a nuclear reactor, and it makes all this steam and spins turbines, and then it goes up through here, and the stuff that comes out is not smoke. It is water vapor. It's condensing steam is all it is. That's how these things work. But what you do is you use something called y'all, shh. You have a large unstable radioactive isotope of uranium-238. And because it's unstable, it's going to break apart. It's going to split. It is going to fissure or crack into something that is smaller. This is the type of nuclear energy that we use to create some of the electrical capacity that in our country. It's like 11% of the energy that we use in this country is nuclear. I don't even know where the closest nuclear plant is. This is this is actually an example of fusion. Is this? No, this is fission. So we have uranium. Now this isn't 238, this is 235, and it's breaking down into krypton and barium. Now you have neutrons on either side. Now we are ignoring from one element to another, whether it is breaking down, which is fission, or if you've got multiple things that are coming together, the neutrons do not count. The neutrons are like a catalyst. That's what starts the chain reaction. Or you've got multiple elements on the left, and they're making one thing on the right, which is fusion. That's what happens in the giant hydrogen bomb in our sky that we call the sun. Okay, but fission is what we do here. Now there is an exception. Okay, when I was your age, I was told that we could not do fusion on our planet or it would like blow up. Yeah, it was a lie because we've had tokamak generators since the 60s. They're like giant donuts, and they're literally creating what happens inside our sun, inside this colliding, this it's called a tokamak. They're just not good at the amount of energy that goes into what they can produce. They're nothing like these guys. So no, it's not hadron collider. It's not like CERN. No, it's called a tokamak. I get into those a lot in my space unit in the very first 6 weeks in our space. Because like I said, I was always told that we would not be able to do fusion here, only fission. That is a lie. I don't know where the closest tokamak is. I know there's one in China. The original ones are Russian. We have to have one here. We have to. Of course they did. The tokamak is Russian. It's a fusion generator. It recreates what happens inside the sun for energy. All right, now this reaction where you have an incoming neutron that starts the chain reaction. Okay, so you have uranium-235, which is this guy, okay, and it's breaking down into barium-141 and krypton-92. Now these are also unstable because they're too big. And you have these neutrons are going to be kicking off. Look at these 3 neutrons, which, like I said, we are ignoring those on this paper, completely and totally ignoring them. But that emitted neutron kicks off a different uranium, whether it be 235 or 238, into the other smaller bits. The whole reason why these things break down is because there's too much stuff in the nucleus. It's like putting too much water in a water balloon and it's going to pop. Okay, but that last drop of water that makes the balloon pop is a neutron from a previous fission reaction. So the neutron plus element is not fusion, it's fission. It's just a chain of events. You have one that kickstarts it, it produces 3. Those 3 will kickstart 3 more, 3 cubes, so you're going to have 9 after that, and it's just a cubic thing. I'm not going to make you calculate that kind of stuff. You will in college if you go off to take this in college. But it is a chain reaction. This kicks off 1, 2, 3. Each one of these would kick off 3 more. This one would go off to another uranium. So you have 3, 6, and 9. Each of those little baby neutrons that get kicked off would create 3 more at a time. So if you take chemistry in college, or if you go into like thermochemistry, which I never did, then you're really going to go into this kind of stuff. Oh, the other thing that was on here. So like, you've ever seen the footage of the nuclear bombs that were dropped on Japan, the big mushroom cloud? It's this exponential growth that creates that mushroom cloud. In this core, you have these uranium rods that are immersed in water. If they're not immersed in water, they're gonna get so hot, they're gonna melt down, and it's gonna be something like Chernobyl if you did that nuclear gallery walk. Chernobyl didn't just melt down, it exploded. And it wiped out, I don't even know how many people. I'd have to look it up. I know that the fallout went as far as Spain. So, and Ukraine is quite a ways away from Spain if you know any of the geography. But in this case, you have to have a certain amount of nuclear material in the core, which is called critical mass. If you don't have enough, it isn't going to be able to do its job. And where it happens is within the reactor. This is not the reactor. This is the cooling tower. Like I said, that's not smoke. It's cooling water that came in that helped keep this reactor cool, produced steam, spun the turbine, was sent off to either a battery or directly to go let people turn lights on and off. That's how these things work. It's a very simplified version of how these things work, but that's how a nuclear reactor works. I don't know if you guys took IPC or not. They're supposed to teach you about that, but IPC is one of those classes that's like going away, and then it came back, and I don't know. If it's controlled, it's one of these things. If it's not controlled, it's an atomic bomb. Okay, so like I said, we're the only one that's dropped atomic bombs. We've done it twice. And one was plutonium, and I can't remember the other one. They were different materials. But when they detonate, it is a runaway train, and that's what creates the mushroom cloud. That isn't going to happen with one of these. These things are controlled by computers and all different kinds of stuff. Unfortunately, with Chernobyl, the computer failed. The 2 techs were sent in to try to manually shut down the reactor, and they died almost instantly. And it blew up, and it killed a bunch of other people. Chernobyl. The one that happened in, no, it was 80-something, I thought. That sounds right. 3 Mile Island was 79, but it didn't actually melt down. The people that were sent in were, because when the computers fail, you have to like manually turn the knobs and push the buttons and whatnot, and they stopped that one. That actually happened not too far from where I lived. I was 1.5 when that happened. I was young. I mean, I don't remember it, just I know what my parents told me. Everybody freaked out for obvious reasons. Right, fusion. But it didn't explode. It didn't melt down. They stopped it. They stopped that chain reaction from occurring, which they did not do in Chernobyl, which is why it literally exploded. And unfortunately, the elephant's foot that's inside it is aerating, which is bad because it's still radioactive. It's still being, it's changing from the solid form to I don't know, is it me going off? Whose phone is constantly going off? Mute your phone.
Isn't it weird how it can be functioning like nuclear?
Yeah, that's what I haven't completely and totally researched all that, but I do know that because the elephant's foot's like a molten, like, but then frozen in time kind of thing. But it's literally turning to dust, and it's getting into the air, which is because it's not done doing its thing. The half-life of uranium is insane. We use uranium to date like meteorites that are 4.6 billion years old. So it ain't going to stop doing its thing for a long time. Fusion, on the other hand, this is what happens in the hydrogen bomb in the sky that we call the sun. They take 2 smaller elements. In the case of our star, it takes hydrogen, and it's going to, under intense heat and pressure, make the next element, which is helium. That's how our star does its thing. That's why it's the color that it is. When they start taking helium and making the next one up, which is carbon, they turn white. And they take carbon and make the next one up, which is, iron is red. That's the one, I can't remember what color silicon is. But if it's, no, there's just the same as a black dwarf. I mean, the youngest of the stars are blue, but anyways, that's Earth space. But you have 2 smaller elements that come together, not neutrons, this doesn't count, okay? Not a gamma, not a beta, but 2 different elements that come together to make a new element. Yes, sometimes they do give off something, in alpha, beta, gamma, but those don't count as far as what we're doing today. We're ignoring all of that part. The thing that these 2 things have in common, fusion and fission, is they give off energy. Fusion gives off way more energy than fission does. Our problem is we're having a hard time getting the energy out that we put in with a tokamak, which is one of these. This is called tritium. Okay, this is called deuterium. Those are actually supposed to be superscripts. They are not supposed to be coefficients. Here, let me fix it. They're supposed to look like. Are they like that on your paper? Are they superscripts? Yeah. When I pasted it, it didn't transfer right. It never transfers right. Ever. Who's that? And then this image. Okay, so there are 3 types of hydrogen. There's protium, which is just a proton, no neutrons. That's normal old hydrogen. There's deuterium, which is a proton and a neutron. This is what we use to make what we call heavy water, like the original atomic tests heavy water, because it's twice as heavy as regular hydrogen. And then tritium, which is unbelievably unstable, which has a proton and 2 neutrons, so tri meaning 3. That's where those actually come from. But when they all come together, you do have a neutron that's expelled, and your helium nucleus is 2 protons and 2 neutrons. And it gives off a whole bunch of energy. This is the background for the atomic bomb. Now, the ones that we dropped weren't this. I know one was plutonium. I can't remember what the other one was. And I can't remember which one was Fat Man and which one was Little Boy, because that was the names. They were different. They were totally different technology. And thank goodness the German physicists came from Germany over here, or Hitler would have had the bombs. But they could see what he was doing, and they left. And they came here. Oppenheimer and I can't remember the other scientist's name. Oppenheimer was one of them. Fusion comes from stars. Okay, our star is named Sol. We call it the sun. That's why we're called the solar system. Okay, but stars are nuclear reactors. They're what makes the other elements. It's the whole. If you've ever heard the phrase "you're made of stardust," it's true, because the stars are what changes hydrogen into everything else, and then they go. And then they make the heavier elements, and they get spread out through the environment, and somehow we ended up here in this corner of the world. The uncontrolled version is an atomic or a hydrogen bomb. Okay, like I said, there's different types. There's different types of nuclear weapons too. This is the problem when tokamaks are not being used yet. We're hoping that we can harness those for stellar travel. We haven't gotten there yet. We still, the 2 satellites that are interstellar right now, the 2 Voyagers that were lobbed out in '77, they use this type. They have fission reactors on them, and they still are going strong. Is there one more on here? There is. Is it on this one, or is it on the next one? No, it's not. In order to trigger fusion, you basically have to have an atomic bomb. I think that's on the next slide. It's not on here. I bet you it's on the one we do Monday. But like I said, this is still expensive to do, but it's way cheaper than the fusion reactors, which we do have. It's just, it's this. They're not efficient yet. So we're working on it. We've been working on it for 70 years now, 60 years now. One of the big problems in my Earth space, we actually are they're testing over this right now. You have to dispose of spent uranium ore properly. They basically put it in barrels. I don't know where the heck they put the barrels, probably out in the middle of the desert, and they bury it. Because I know they don't put it in the ocean. They would put it where people don't live. Oh, I didn't. Okay, well, here's I did not animate this. All right, so you guys have a Venn diagram. The things that they do have in common is they both deal with the nuclei of atoms. Okay, one of them joins them together. The other splits the nucleus apart. They both produce energy. Okay, fusion happens in the sun. These are in our hydrogen or atomic bombs. Fission, this is what happens in our current good, like not the tokamaks, the nuclear reactors. And this would be an atomic bomb. Atomic bombs and hydrogen bombs are not the same thing. They are not the same thing. You would have to use an atomic bomb to trigger a hydrogen bomb. It takes that much energy to be able to kickstart it. So, and like I said, we're the only country that's thrown atomic bombs in other countries. Did it twice. World War II. We do have other nuclear weapons, but as far as these, there is the, what's it called, the Tsar Bomba, most powerful of all of them, never been used. We have MOABs, but those aren't atomic bombs. They're just nuclear weapons. Mother of all bomb is what MOAB stands for. We could go into all different kinds of weird depth with nuclear weapons, and I don't know if we're going to have time. Here. Make sure you guys. And there's one more thing that we're going to do. Okay, I need to show you how to do these problems. We're not doing like a specific. Listen, I don't think we're doing a specific one on here. If I have it on the next slide, it was accidental. Oh, great. Coworkers are blowing it with phone. Let's see. Well, it's if they're texting me, it has to be work related. Caitlin, Logan, Jared. Yes, go here, do not walk. They're checking the cameras, and the camera's right there at the end of the hall. Braden, see what, for those of you, let me check online. Oh, nothing, I'm just talking to myself because I'm doing too many things at once. Okay. All right, we got one more thing I want to show you how to do. How easy these problems are. If this is not on your paper, you're more than welcome to write it down if you want to somewhere, because this is how you're going to do the assignment. With fission, okay, now I gotta give you the numbers. With fission, you have one larger element, in this case is uranium-235, and it's going to break down to multiple things. Normally it's 2, sometimes it's 3. Doesn't matter how many things are on the right, but all the things on the right have to equal to the thing that's on the left if it's fission. So if uranium starts off with 235 and goes to 231 on thorium, and the atomic number goes from 92 to 90, let's do the bottom number. What's 92 minus 90? 2. What's 235 minus 231?
4.
What element is this?
Yeah.
This is helium. This is alpha decay. You're literally doing what we did before. And like I said, we're ignoring the incoming neutrons or the beta, or in this case, the outgoing would be an alpha decay. And there might be more than one element on either side, depending on what we're doing. With fusion, I got to give you the numbers. You're going to add them together to make something new. Okay, so let's 13 plus 1 is,
14.
and 6 plus 1 is.
7.
How do you know which element this is?
7.
Which one's 7? That's nitrogen. This is regular old nitrogen. It's not any weird isotopes or anything. Y'all, that's all you're doing on this paper. And we've got 20 minutes in here. Okay, so if there's one thing on the left, it is breaking apart, it is fissuring, it is cracking, it is fission. If you have things that are coming together, they are fusing to make one. This is fusion. That's how you tell them apart. That's all that paper's doing. And you're going to probably need a periodic table if you need to look up which element it is, and it's the bottom numbers that tell you which element. It's not that bad. Now, so keep in mind, I am not here Monday. I'll be here Tuesday. I'm going to, while my other classes are taking their test, I'm going to make sure that these nuclear chemistry assignments, the gallery walk, the one that was similar to this but was two-sided, and this one are all available at least through 11:59 on Monday. So did you have one to turn in or multiples to turn in? I will also put behind, which I've not done yet, but I will do today, the list of what should be in your notebook. The only thing you're not going to have is notes 54. because we're doing that Tuesday. So if you've been doing paper notes and you're caught up, start taking pictures and uploading them and putting them into a file. Your notes, let's see, Tuesday we're doing notes 54. Wednesday we're doing a Google slide of all of nuclear chemistry. Thursday we're reviewing for Unit 12 test. Unit 12 test is Friday. So you're going to have the information to be able to do your notebooks. The only day that I can actually give this class time, if you have issues submitting your notebook, is not like Monday the 17th, but what is the next Monday, the 24th? You need to make sure that you take it off of restricted. Your notebooks have to be turned in the class period on Monday the 24th. Because if I can't see it, like I don't have access, or maybe you only gave me one section, you didn't give me all of them, that's the only day that I can tell you. We are even. So our CBA is seniors, even is Monday. You guys mostly are not seniors, so you're going to have your odds on Tuesday. And then evens would be Wednesday, and then there's a half day Thursday, and that's the last day of school.
Yep.
And that's meant for like people who missed their test. So that's the real. Is there any question how I figured out what was missing on these? Because that's what the assignment is. You're either adding or you're subtracting. That's all you're doing. You look confused. On the first one. Okay, so if it's breaking down, okay, something over here is going to add to this to make this, and its bottom number is going to add to this to make this. So 91 minus 77 is the bottom number, and 31 minus 192 is the top of this. And then whatever the bottom number is, you look it up on the periodic table. Okay, let me do official attendance and figure out what my coworkers want real quick online, because I am missing people, and I need to check online. Let me stop my recording.